Hi everyone. If you're new here, my name is Ryan, and today I'd like to go through the solution to this FE exam fluid mechanics problem with you. You can try the problem for yourself first before you watch the video solution to refresh those concepts in your head. You can use the first link in the description below to do that. It'll take you to a screen just like this where you can solve the problem for yourself. You can come back here and watch the solution. Let's get into the solution now. I'm going to transfer straight to a clean sheet of paper here because there's a lot of givens in this problem, and I want to take them down now. So it says the volumetric flow rate, water is flowing at 1.75 cubic feet per second. Volumetric flow rate because it's cubic feet per second, a volume for unit of time. We're given a diameter here of 5 inches. Now water is flowing through that pipe. That pipe length is 160 feet long. And it's connecting two large tanks as shown. The pipe, it has a roughness value of 0.002 inch and a kinematic viscosity value of 1.08 times 10 to the negative 5 feet squared per second. It says neglecting minor losses, the elevation difference, h. What is that h value equal to? Okay, a lot of things in this problem. We're given a few different givens. First thing is that we are looking for that height h. If I'm thinking about what kind of equation can I use to bring into the problem the elevation, I'm also noticing that we're given this E value, a roughness value for the pipe that's associated with friction losses. So I'm thinking that we need to use the energy equation. And what the energy equation says is that basically this equation here, P1 over gamma plus V1 squared over 2G plus Z1. The energy equation is almost exactly the same thing as Bernoulli's equation, but there's an additional term here, the head loss due to friction. Now, the head loss due to friction can be broken up into two terms. There's a major loss term, and there's also a minor loss term. The minor loss term are due to pipe bends, elbows, entrance effects, like what we have here when we're flowing into this reservoir. What the problem says is that we want to neglect those minor losses. So we don't have any minor losses, but we do have a major loss. The major loss is associated with friction losses due to a straight length of pipe. Okay, so it looks like we have this. And if we want to see where we got this in the manual, we can go ahead and do that. Okay, so we see the energy equation here. That's this. This is head form, so all of these terms have units of length. And this is pretty simple. I like this kind of this kind of form of the energy equation. We're going to make some simplifications later, but you see we have a friction loss term and we also have an elevation term, so it's going to bring into the problem that h value that we're looking for. So we have that. Also, we know that the volumetric flow rate is the area times the speed. That's going to come in a little bit later. And you see Bernoulli's equation on the bottom. So that's where we got the energy equation information. This head loss due to friction, the major loss, it can be found using this Darcy-Weisbach equation. So that's what we're going to do in this video. What we need is the friction factor, the L over D, and the V squared over 2G value. The friction factor is found using the Moody diagram, and the Moody diagram relates as a dimensionless chart that relates the Reynolds number relative roughness to this friction factor. So we're going to end up using that Moody diagram, and it's at the end of the fluid mechanics section, which is this. You can see on the x-axis we have the Reynolds number. We have a relative roughness value. That's a dimensionless term. It's that roughness that we're given divided by the diameter. We kind of go up knowing the Reynolds number to a certain relative roughness value and move over to the left to get that friction factor value. So that's our general plan for this problem. Let's see if we can make some simplifications here. Firstly, we need 2 points to be able to use the energy equation. Let's say point 1 is the top and point 2 is the bottom. And I made it this way because this is the way that the flow is going to occur. There's no pump in the system. So that means we're not going to be going from the low reservoir to the high reservoir, but naturally we want to flow from that high point to the low point. Okay, because we have a large reservoir, what that means is that the surface, the surface height is not going to change much. That's because it's so large that the tank is going to drain very slowly. That means these points on the surface, point 1 and point 2, will have negligible speeds. And this is a pretty classical assumption when it comes to these reservoir problems. And if you don't get a problem like this on your FE exam, you'll most likely get a reservoir problem, maybe not on the energy equation, but maybe Bernoulli's equation. So these kind of assumptions are important to know. So make sure you understand that point 1 and point 2 have a zero value speed. They're draining very slowly. Their pressures are also atmospheric or zero gauge. So all of these terms are going to be zero. Those 2 points on the surface are exposed to the free air, right? So they have atmospheric pressure. Atmospheric pressure is the same thing as zero gauge pressure. We also have these elevation terms. If we make our datum aligned with that point 2, the lower point, we can kind of get rid of this Z2 value. And what we get is the Z1 value is just equal to the height H. That height H is equal to that head loss due to friction, the major loss. That's just equal to F L over D, V squared over 2G. We said that we can get this F term here using the Moody diagram, but we have to know the Reynolds number as well as the relative roughness. Let's go ahead and make those calculations now. The Reynolds number is just the speed times the diameter divided by the kinematic viscosity. It's a dimensionless term. So you see here, we're not given the speed, but we are given the flow rate. We know that the flow rate is just equal to the speed times the area, or we could solve for the speed doing the flow rate divided by the area. Now, I hate solving for things that I don't need, and you don't really have time to on the FE exam. So I usually try to use algebra to use my givens without calculating anything I don't need. I don't need that speed term, so I'm not going to calculate it. If I replace the area here, which is pi d squared over 4, what I get is 4q divided by pi d squared. So I'm going to substitute that into the Reynolds number. I have a diameter term that's going to cancel out with one of the d's on the speed term. What I get is 4q divided by pi d nu. If I go ahead and plug in what I'm given, I know the volumetric flow rate is measured in cubic feet per second. There's a pi term. The diameter is measured in inches. I'm going to convert that to feet by dividing by 12. And then my kinematic viscosity, that's also measured in feet and time, so those will cancel out the units. 1.08 times 10 to the minus 5. If I go ahead and plug this in, let's see what I'm going to get. My Reynolds number is equal to 4.95 times 10 to the 5th. I usually write it like this because on the Moody diagram, we have powers of 10. There's a log scale on the bottom. So you want to have that times 10 to the 5th or 10 to the 6th or whatever you have. You want to write this in scientific notation. It makes the diagram easier to read. The next thing we need is that relative roughness value, the E over D. The roughness was given as 0.002 inch and the diameter was 5. What that turns out to be is 0.0004. Lots of zeros there. Okay, so the next thing that we're going to do is knowing the Reynolds number and the relative roughness. We're going to go to our Moody diagram in the FE exam manual. Now 4.95 times 10 to the 5th, that's approximately 5. So it's where my mouse is, right? Between 10 to the 5th and 10 to the 6th, we have this 5 times 10 to the 5th term. We're going to go up until we reach this value, 0.0004. Now that's this point right here, and we'll just travel straight to the left. So it looks like we're around here. Each of these little lines here are, looks like 2, so this is 10, 12, 14, 16, 18, 20. We're right around here between 16 and 18. I'll call it 17. So our friction factor is F 0.017. Okay, now we're ready to go ahead and plug in all our numbers. Remember that speed term was just 4q over pi d squared. If we just write down quickly what the speed square term is, that's 16q squared divided by pi squared d to the fourth. Now what I'm going to do is plug in everything here. I have f L over d. I have a 2g term in the denominator, and I also have that v squared term, that's 16q squared divided by pi squared d to the fourth. I'm going to go ahead and make some simplifications here. We have f, L, we have a 16 and a 2 here. That's going to cancel out to make an 8. We have a d to the fifth. Here's an 8q squared divided by pi squared. There's a d to the fifth and a gravity term. Let's make sure this is correct. 8f L, there's a q squared in the numerator, d to the fifth in the denominator, pi squared and g. Okay. Now that we have all of this, let's go ahead and plug in. We have that f. We found that from the Moody diagram, 0.017. The length was 160 feet. Multiply that by 8, and we know our flow rate was 1.75 squared. We have a pi squared in the denominator, a 5 to the fifth, as well as a gravity term. Now this was an English units problem, so our gravity is 32.2. Let's work out all the units. Okay, so the 160 was measured in feet. The 1.75 was measured in cubic feet per second, but that's squared, so it's feet to the 6 over second squared. We have an inches to the fifth in the denominator and a feet per second squared. We know that there is 12 inches in a foot, and that's raised to the fifth power. How do the units work out? We have all the feet end up canceling out, the feet to the 6. There's a second squared, and the inches are gone. We're just left with feet, which makes sense. We're looking for height in feet. Let's go ahead and calculate this out. We have that 12 to the fifth in the numerator, so make sure you include that in your calculation. And we end up getting approximately 16.7 feet. Let me know in the comments below if you're able to get this answer. And if you're enjoying this content thus far, please leave a like and subscribe. It really helps me out a lot. Let's go ahead and check this answer. Also, if you're interested in, if you enjoy solving problems like these, definitely check out my my prep software, FE Interactive, where you can gain access to a bunch more problems like these, as well as analytics and calculator tips. Okay, so 16.7 is what we got. Let's view the explanation and quickly just go over what we did. Now, what we did was we used the energy equation with some common simplifications for reservoir problems, like the pressure terms were 0, as well as those speed terms, right? The surface of the water was barely moving, and the surface is exposed to the atmosphere, so 0 pressure, 0 speed. We made 0.2 our datum, so that means that our height, h, was just z1. We set that equal to the major loss. We neglected the minor loss. So we used the Moody diagram, went ahead and found the major loss, finding that friction factor term with our relative roughness and Reynolds number that we calculated. We were able to plug into that h value using the Darcy-Weisbach equation and found the height in the end was 16.7 feet. If you enjoyed the video, please leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.